Thank you, Emily.
Okay.
Um, all right, thank you everybody for joining us today. Looks like we've got a pretty good crowd here. My name is Seth Winger. I am the Director of Science of the University of Georgia River Basin Center, and it's my pleasure to be hosting this Fall 2014 Cyberseminar series, Sustainable Urban Streams, Science to Support Evolving Management Objectives. Today we have the fifth and final Cyberseminar in this series from Ann Jefferson. Dr. Jefferson is an assistant professor at Kent State University in Ohio. Prior to moving to Kent State in 2012, Jefferson spent 5 years as an assistant professor at the University of North Carolina, Charlotte. She holds a PhD in geology from Oregon State University, an MS in water resources science from the University of Minnesota, and a BA from Johns Hopkins University. And without further ado, I will turn it over to Ann Jefferson.
All right. Thanks, Seth, for the introduction. If you can't hear me, I suppose you should type something in. So I think that's called preaching to the choir. So today I am very honored to be able to present the final seminar in this series because all the speakers who preceded me have done an outstanding job of laying out a high-level overview of the issues facing urban streams. So the picture that we're looking at today, I think, gets at the heart of the topic that I want to focus on, which is the connections between stormwater and the responses we see in streams. This is the sort of beautiful stream that I think drew many of us to studying hydrology in the first place. This is West Creek in northeastern Ohio. But if we zoomed up from this stream level view of the creek, what we'd see just up on the hilltops is that this stream is completely surrounded by urban and suburban Cleveland. And it is, in fact, heavily impacted by stormwater runoff anytime it rains. So if the goal of the seminar series is to understand the science that might help us get to sustainable urban streams, I would put forward that this is one of the many poster children that we should be aiming to protect and improve. So often when we think about urban streams, the ecologists have given us this nice term, urban stream syndrome. And it relates to a variety of impacts from urbanization on channel form and function, on the biogeochemistry and contaminant loading into streams, and on the ecosystems that are impacted as a result. And these sorts of impacts can range from this sort of alteration of channel morphology and riparian zones to some more severe impacts. If you want to keep your stream clean, don't put in a washing machine, all the way to the complete burial of urban streams. But at the root of these many changes we see manifesting themselves as urban stream syndrome lies stormwater and the very flashy high flows that you see associated with stormwater runoff into the urban streams. So that, I think, is why my focus is stormwater stream connectivity. All right, so the US EPA defines stormwater as rain and melted snow that runs off streets, lawns, and other sites, which sounds actually not too bad. As hydrologists, we might think of stormwater as overland flow, Hortonian overland flow, and water that is then unavailable in the watershed for either infiltration or evapotranspiration. We also need to recognize that this stormwater is coming into contact with all of the things that we put on our streets, lawns, and rooftops, so metal loading, excessive nutrients, and that the stormwater then takes that to the streams itself. So I would argue then, most of the time, stormwater becomes a problem at the point at which it reaches the stream. And I've listed down at the bottom of this slide a number of the sorts of impacts on urban streams that we can attribute to stormwater. Now, there are important exceptions to this. I think our previous speakers have shown that the impacts of stormwater on groundwater or on sewer surcharge can be a real problem. But much of our focus really is on the stormwater stream connection. So therefore, think that we are facing something that I would estimate on the order of a $10 billion a year question in terms of how do we manage stormwater. Now, this $10 billion number is rough, but based on what I can find about consent decrees forced by the EPA, bits of industry in various parts of the U.S., and public utility spending, it seems about the right order of magnitude for the amount of money we're talking about when we're talking about stormwater management in the U.S. alone. So the $10 billion question then, one way we might phrase it is something like, how can we mitigate stormwater in order to minimize risk to human health and infrastructure and protect aquatic ecosystems? So we need to focus on both the built environment and our presence within the watershed and the natural environment that we would want to protect. So over the last few centuries, we've tried various approaches to answering that question. The sort of earliest approach to stormwater management I like to call the put it in a pipe and get it out of here approach, which we still see practiced today. These are two examples in my neighborhood of a pavement pipe stream system. And I think we can all agree that this fails the test of minimizing risks to human health and infrastructure and protection of aquatic ecosystems. A slightly more sophisticated approach that was practiced up until the early 20th century was that of building combined sewers. Now, in combined sewers, you have both your sewage going from your toilets and houses and your stormwater coming from your streets and rooftops, all going into the same sets of pipes. Now, when it's not raining, or when the rain intensity is low enough, all of that water is piped to a wastewater treatment facility where it is then discharged into a stream, lake, or other receiving water body. The problem really comes in when we have intense rainstorms, because at that point, the pipe network and the sewage treatment plant is above capacity, and what happens is that we overflow and a mixture of stormwater and untreated sewage goes out into the receiving water body. So again, fairly easy to understand that this does, when these overflows happen, that we are really not minimizing risk to human health or protecting aquatic ecosystems. So the modern solutions to stormwater management are focused in kind of three areas. Stream restoration, which I'm not going to talk about today, usually is focused on sort of healing the urban stream syndrome symptoms without treating the stormwater cause. Although sometimes some of the elements of stream restoration, people at least claim that they're helping with stormwater management. The two main approaches are fairly centralized stormwater control measures like constructed wetlands and ponds, often built fairly close to the stream, collecting runoff from a large area and then storing it for some period of time and releasing it more slowly into the stream. And the idea of green infrastructure, which is distributed throughout the watershed, often treating small areas of land for any one piece of infrastructure, and often has an element of both infiltration and evapotranspiration. That's why it's green infrastructure. So the question then for us as modern hydrologists are, how are we doing today? How is green infrastructure and stormwater control measures doing at minimizing risk to human health and infrastructure and protecting aquatic ecosystems? So how are we doing at managing stormwater now? I would suggest that in order to answer that question, we need to focus on the other portion of my talk title, which was context, processes, and trade-offs. And so that's what we're going to start to examine each one of those things now. So when I'm thinking about context, I'm taking a engineering solution like a stormwater pond or wetland or piece of green infrastructure and citing it within the broader picture of the watershed or the landscape. So what are the factors surrounding our engineering solution that might influence how effective it is at managing stormwater and doing those ultimate goals of protecting humans and aquatic ecosystems. When we think about stormwater management, and a lot of the engineering approaches to stormwater management draw on what's shown here that I would call the conventional view of urban hydrology. So we increase impervious surfaces, we reduce groundwater recharge, we increase stormwater runoff, increase peak flow. I would argue that that view of urban hydrology, while right in many ways, is perhaps oversimplified because it neglects this important piece of context about the landscape, the style of development, and in fact, even the sort of social forces acting on urban watersheds. We could complement, the top image is that same view of urban watersheds, where we are reducing groundwater recharge and increasing peak flow. We could complement that with an additional set of processes happening in urban watersheds, things like reducing evapotranspiration, leaky infrastructure, adding water to the system, importing water across basin boundaries, all sorts of processes that might, in fact, increase base flow and increase groundwater recharge in urban environments. So which of these pictures, top or bottom, is dominant, and what elements of each one that we need to include when we're thinking about how to manage a particular urban watershed is going to depend on the context of that watershed. For example, natural setting, the things that we think about as physical scientists, soil, bedrock, climate, and vegetation can have a huge impact on what we see happening in terms of the magnitudes of peak flows that result from urban development, and also at the other end of the spectrum, what happens at base flow. So just thinking about within the southern US, within a humid subtropical climate, we can find some pretty contrasting examples within the literature. For example, in Atlanta, we've shown that base flows decline 30% as a stream gets urbanized. But John Sharp and his students in Austin, Texas, have shown that urbanization actually results in a pretty significant increase in groundwater recharge and therefore in stream base flow through all those things like irrigation, leaky infrastructure, and cracked impervious surfaces that allow a fair bit of recharge through them. So the difference, the fundamental difference between Atlanta and Austin is not so much the style of development, but the fact that Austin is sitting here on the highly permeable Balcones escarpment, a nice limestone landscape, whereas Atlanta is sitting over here on a much less permeable landscape. And I'm sure you can imagine that if we expanded past the southern US, we could think that the way stormwater and urbanization get played out in a place like Atlanta or Baltimore might be quite different than a place like, say, Portland or Seattle, just because of these differences in bedrock and climate, soil, and vegetation. But it's not just the natural environment. I'm fond of saying that if we're thinking about urban watersheds, we're really squaring the complexity. We're making it as difficult as possible, because we also, on top of all of those differences and heterogeneity in the natural environment, we have to think about what's going on in the built environment. Oftentimes, our focus in urban hydrology is what happens when we develop a new piece of the landscape. If we design a subdivision, how much stormwater control do we need to put in? But we also have the already built development of the inner parts of our cities. For example, the lower right image of Parma, Ohio, which is a Cleveland inner suburb, shows that it's an extremely densely developed suburb, was developed prior to any sort of stormwater control, and trying to figure out how to manage stormwater in a landscape that looks already like this is quite a different matter than trying to figure out how to manage stormwater development when we're still allocating out the parcels of land that houses and other developments will be built on. At a larger scale, we have the contrast between areas with growing populations versus the areas with shrinking populations and high rates of vacant land. So Cleveland and many other older cities are sort of hollowing out in many respects. Population in the city center and inner suburbs are declining, and we are seeing a lot of abandoned houses and vacant lots developing. And yet in the outer belt of suburbs, we see population increasing in many places. So how we think about stormwater management in a place with a growing population and expanding footprint is quite different than how we think about stormwater management in a place where suddenly we're getting new vacant lots and new potential spots to retrofit stormwater controls into a fully developed watershed. We also need to think about how the particular land use types within a watershed may represent different opportunities or challenges for stormwater management. In the lower left, I've put in a picture of one industrial site in Cleveland. This site is 62 acres, and it is 57% impervious. This dark blue rooftop that I'm pointing at right now is 6 acres in size itself. Well, 6 acres in size is someplace between 25 and 50 urban residential lots in a lot of neighborhoods. So if we can work with a single landowner to do something about stormwater being generated from that single rooftop, we might have a different level of ability to get something done, ability to try something innovative, and ability to really reduce our stormwater inputs to the local watershed just at that one site than trying to do that at the scale of a street or a subdivision. And then I didn't put this specifically on the slide, but I wanted to also make the point about protection of riparian zones and the direct connection between the surfaces generating stormwater and the receiving streams. If we stay at that industrial site, there is actually a buried stream underneath that industrial site receiving direct stormwater input with no possibility for any sort of riparian buffer to that development impact on the site. Conversely, in Parma, as densely as the uplands are built, because of the topography around there, the headwater streams and the larger trunk streams have fairly forested riparian zones, which may afford a different level of being able to manage stormwater input. Although the topography does limit sort of just being able to go in and retrofit stormwater ponds and wetlands. The infrastructure of stormwater itself is also incredibly important, and I want to come back to this because this was something that I didn't pay a lot of attention to until I moved to a place with combined sewers. So in modern developments, we have our sewage from our buildings going to the wastewater treatment plant, and our runoff from our impervious surfaces going into a storm sewer network, which hopefully passes through some sort of stormwater management infrastructure before outfalling into the river. And when we are in dry weather, there's nothing in that storm sewer network. When we're in wet weather, the stormwater stays stormwater and the sewage stays sewage. In the combined sewer systems, again, you have a single set of large pipes underground, and in the wet weather, we see this commingling of sewage and stormwater, a lot of it making it to the wastewater treatment plant, but some of it outfalling to the river. So this is not just a Cleveland-specific issue. There are 772 U.S. communities that are served completely or in part by these combined sewer systems. And the way we have to think about managing stormwater in a combined sewer system might be quite different than managing stormwater in a separated sewer system. Again, we can't just put a stormwater pond at the outfall of the pipe, because in wet weather, that stormwater pond would then be also receiving some element of untreated sewage. This is also one of these places where we see big infrastructure investments going on. For example, Cleveland is under a $3 billion consent decree from the US EPA to reduce our combined sewer overflows by 98%. And Cleveland's not the only place. Washington, D.C., Philadelphia, Chicago, Akron, all of these cities are under extremely expensive consent decrees from the US EPA to really solve their stormwater problems. Just one more slide on this topic. Again, this is a map of Cleveland, and all of the red locations are places where combined sewer overflows can happen. And you can see that these red locations trace to a large extent, trace the stream and river network in this area. On the outskirts of the map, in the newer suburbs, we have separated stormwater and sewage. But in the sort of pre-1900 core area of development in Cleveland, we have these combined sewer systems. So in wet weather, then, our stream network in Cleveland is really receiving potentially this mixture of stormwater and untreated sewage. But the impacts of these combined sewer systems don't go away in the smaller storms and in the drier weather. So the black stars on this map represent the wastewater treatment plants that serve Cleveland. Now you notice that there are only 3 black stars. That means that under dry weather and under small storms, all of the stormwater falling in most of this map area is only being outletted 3 places into the environment. And 2 of those places are right on the lakeshore of Lake Erie, so aren't making it into a watershed at all prior to going to the lake. Instead, the only place receiving any stormwater, having passed through a wastewater treatment plant at that, is the Cuyahoga River itself at this lowermost star. The rest of these smaller watersheds are then completely deprived of any sort of storm event response or hydrograph, because that water is instead being piped across watershed boundaries and to this wastewater treatment plant. So if you want a sort of profound example of the changes to hydrology that can result from urban development, I don't think you can find something that is more of a stark geographic and temporal change to hydrology than combined sewer networks. Finally, people matter, and it's not just in terms of the infrastructure that we build, but also in terms of the way we manage and think about the stormwater problems and environmental problems in our urban areas. So environmental attitudes in terms of what types of stormwater management might be acceptable to a particular community are extremely important, and I think something that we need to do a better job of accounting for when we are working in urban watersheds. If you are living in a development like this, what I'd call a Stepford-wise neighborhood, the idea of putting in rain gardens or rain barrels might be socially unacceptable, and in fact might even be forbidden under something like a homeowners association clause. Whereas if you're in a neighborhood like this with lots of gardening and lots of personal involvement with the outdoors, the concept of green infrastructure might be a much easier sell. And in some residential neighborhoods, there simply isn't enough green space for people to really have a lot of that sort of hands-on contact with the environment, and again, might be a more difficult place to get people on board with the concept of distributed stormwater infrastructure or green infrastructure. We also have to think about the economic realities and regulatory realities of stormwater management. So we've heard previously about projects in Australia where there was nearly 50% participation in green infrastructure projects, which is fantastic. But they were able to provide economic incentives for those homeowners to participate. Well, here in northeastern Ohio, the regional sewer district launched an ambitious stormwater management program only to have it, I'm not sure how readable this is, but only to have it hung up in the courts. We are currently waiting for the Ohio Supreme Court to tell us whether the sewer district has the authority to levy a stormwater fee to manage stormwater better in their region. And what happened as a result of this is that they'd rolled out a big sort of credits and incentive structure so that people who put things like rain gardens and rain barrels on their landscape, or industrial site owners who work to reduce runoff from their industrial sites, would receive some portion of their stormwater fee back. As soon as that got tied up in court, the interest of people in putting things in their own houses or in their places of business completely evaporated. And so for about a year now, there's been no movement in this region towards any sort of wide-scale adoption of new stormwater management approaches. So all of these things, the natural setting, the built environment, and then the human environment, can have some big impacts on what our possibilities are for managing stormwater and how effective our approaches to managing stormwater might actually be. So let's move on to the second component now, the processes component. And what I'm really interested in here is how do the things that are happening in the watershed, the processes that are happening within our urban development, and the processes that are happening within the stormwater control measure, SCM, for those unfamiliar with the acronym, how those things are impacting the water quantity and water quality received by the streams. So among the many questions you might ask about this coupling or connectivity from a process perspective is, what happens if we can't treat all of the stormwater in the watershed? What, in any of your areas of interest, biologically or ecologically, what are the effects of stormwater inputs on in-stream dynamics? How do they change things like nutrient uptakes or metal loadings or temperature responses? And then what are the differences between these different approaches to stormwater management, the centralized ponds and wetlands versus the dispersed green infrastructure on urban storm flow in general? So there are many things you could talk about under this heading, and what I'm going to do in the next few slides is just give you sort of a sneak peek at some hot off the presses data from various projects that we are working on that start to address the stormwater stream connectivity. But before we do that, just a quick review. In an ideal world, these stormwater control measures, particularly the ponds and wetlands, are designed to intercept stormwater coming from the watershed, store it in a pond or wetland, slowly release it, hopefully with some benefit to water quality because of that storage time or interaction with vegetation within that wet environment, and then release it to the stream, so that we take an urban hydrograph that might have been quite flashy like this, and we make it somewhat closer to a pre-urbanization hydrograph. So the first question we might ask is that in many environments, whether they are retrofit stormwater controls into already developed neighborhoods, or even whether when you're building a new development in a new watershed itself, what if we can't control 100% of the stormwater? If we're not going to get to this sort of hydrograph, what are we going to see in our urban streams? So one of the places that we've been exploring this question is in a series of 4 watersheds in Charlotte, North Carolina. 2 of the watersheds over here on the left had stormwater controls implemented at the same time that development of residential areas and commercial areas was occurring within the watershed. One of them has a series of ponds, you can see here and here, and one of them has a mixture of a quite large pond and a smaller wetland. We also looked at 2 retrofit watersheds developed mostly in the 1950s to 1970s within the urban core of Charlotte, And again, just a few of these centralized stormwater control measures in each of these watersheds. So what do the hydrologic responses of the streams in each of these 4 watersheds look like, given that you can see the green areas are the areas that drain into a stormwater control measure before they reach the stream. The gray and white represent areas that don't receive stormwater control. So gray being impervious surfaces, and the key thing to look at here. So what do the hydrographs look like when we have this sort of incomplete stormwater control? Well, I'm not going to show you the hydrographs specifically, just trying to keep this concise, but what we can look at several metrics. If you look over at the left here at the event runoff ratio, so the ratio of runoff, storm flow to precipitation on the watershed, what we can see is that there is a reasonable relationship with the effective imperviousness. Now, effective imperviousness is the impervious area that is directly connected to the stream, so not treated by a stormwater control. So as our effective imperviousness goes up, our event runoff ratios increase. Now, the colors of the boxes are our 4 study watersheds, and what we see is that for our watershed where nearly 90% of the watershed is treated by stormwater control measures, and we have low effective imperviousness, we have a low event runoff ratio, but where our second highest percentage of watershed treated by stormwater control measures has our highest range of event runoff ratios. So just being able to say, well, we're treating 50% of the watershed or we're treating 25% of the watershed doesn't override the things that are happening in the rest of the watershed. Another metric for looking at this is the time lag between I think this is the centroid of the hydrograph versus the peak precipitation. And again, what we see is that total imperviousness itself, this is now all imperviousness within the watershed, regardless of whether it goes through a stormwater control measure or not, is strongly related to time lag, but the percent of the watershed treated by stormwater controls is not. So the takeaway that I take from this sort of data, and we could show other metrics in other locations, is that even when we have stormwater control in our watersheds, the impervious surfaces are still really driving the hydrologic response we see in the streams. And I apologize for the awkward formatting on this slide, but we can also look at where the water within the urban stream is coming from. So what you are looking at in this graph is on the left axis, we have hydrogen stable isotopes, and those are represented by the colored lines on the graph with the points and the error bars representing individual measurements. And on the right-hand axis, we're looking at discharge in the stream, which is represented by the solid, smooth black line. So this is an example of one of our 4 watersheds, where the blue line represents water coming from upstream. It has passed through some urban land, but then through a large reach of forest. So no particular stormwater controls at that upstream location. And we have a stormwater pond outletting into the stream represented as the purple time series. And then downstream, where the water in the stream represents a combination of the upstream water and the stormwater input. And again, that stormwater input has gone through a pond at this point. And so the isotopes are representing a mixture at each time point. So we have upstream, we have the stormwater control measure, and then our downstream water nicely shows the mixing of those 2 sources. We can see also here how at the beginning of the event, our stormwater control pond is not turning on until partway through the hydrograph, and then it's releasing water that's quite different from what the stream is seeing. We see that early in the rising limb and at peak flows, the stormwater pond is doing what it's supposed to. It's storing the water, and we're not seeing a change between upstream and downstream isotopically. But as we get after peak flow in the event and all the way through the recession curve, then our downstream water represents this mixture between the pond water and the upstream water. And if you do a hydrograph separation of this data set, what we see is that over the course of the whole event, about 19% of the water in the downstream stream is coming off of this stormwater control measure, coming off the outlet of it. But that stormwater control measure is draining less than 10% of the watershed area. So the influence it's having on the receiving stream in terms of just the quantity of water is about twice what it should be on a per area basis. And we can imagine, so we've used isotopes as a tracer here, but we can also imagine that the temperature signal or biogeochemical signal of water coming out of that stormwater control measure might be quite different than what is coming through from the upstream portions of the watershed. So this is just one event, one watershed, but we can see clearly how stormwater control measures and stormwater inputs might be disproportionately affecting urban watersheds. And we can also see that coming up in some of our water quality indicators. So this is just an example using temperature. So if we have an urban watershed with untreated stormwater being outlet into the stream, there is widespread documentation that this can cause temperature surges within urban streams as rainfall falls on heated impervious surfaces and makes its way to the stream. So our question is, what is adding stormwater wetlands and ponds between our impervious surfaces and our stream due to the temperature response? So this is the same watershed we were just looking at. If we look at temperature surges in response to precipitation over a series of storms, we see little difference upstream of the pond and downstream of the pond. But we see that the pond itself can outlet water that has a large range of temperature responses. So in this case, the pond or the stormwater control measure outlet doesn't seem to be having a large influence on the downstream response. This upper graph on this slide just shows a single event from that same pond. So we have the pond itself here being warmer than the stream and showing a sharp increase in temperature at the onset of precipitation. We have the stream, which again has come through a forested area prior to reaching the suburban development, having a more delayed and gradual response temperature-wise to precipitation. And we see the downstream of that mixture of the upstream water and the pond water really showing very little response to the temperature surge from the pond. So that's good news. The next watershed over, same rain event, is quite a different scenario. Here we have a large inline pond, and the outlet of that is our upstream time series here. And so what we actually see at the onset of precipitation is a slight decline in stream temperature. But what I really want you to focus on is what the wetland is doing, where again we see that spike in stream temperature. And this wetland, then downstream of it, the stream itself has a huge spike in stream temperature because the wetland is treating so much of the watershed area. 40% of the watershed is passing through that wetland. There's no cooling able to happen within the wetland, very little storage time, and what we see then is this really dramatic temperature signal within the downstream receiving waters. Again, temperature is our proxy here, but we could imagine you can measure this sort of response in any number of variables of interest. All right, so to sort of take that one study with lots more variables to come and more sites to come, what we see is that stormwater control measures are not succeeding in overriding the impervious surface signal that we see in our hydrologic response. And at the same time, they can impart a quite distinct temperature or biogeochemical signal on the receiving waters. So that combination of things sort of suggests that in many situations, these centralized stormwater control measures alone are not going to restore the ideal pre-development stream water quantity and quality. So if these centralized features leave something to be desired, what about distributed green infrastructure? And again, the goal here is to have many smaller pieces of green infrastructure spread throughout the watershed and really a focus on soaking up and storing water, according to the US EPA, and also evapotranspiring water, putting the green in the green infrastructure. So we have another project on West Creek in Parma, outside of Cleveland, where we are doing a paired watershed study with a green infrastructure retrofit on 2 treatment streets where homeowners were solicited to install rain barrels, rain gardens, bioretentions free of cost. And the control streets were left unchanged. So what we have here is we have some pre-treatment data. In 2012, we began monitoring. There are 2 sets of these streets, 2 controls and 2 treatments. And then in May 2013, on 1 set of streets, we installed bioretention cells that are picking up mostly street runoff. And many of these bioretention cells had underdrains. At the same time, rain barrels were put in participating houses, and several homeowners installed rain gardens or had rain gardens installed. The following summer, a year later, more street-side bioretentions were installed, this time with no underdrains, and some more front yard rain gardens picking up roof runoff, and some more rain barrels were installed. On our other set of experimental streets, the homeowners had previously been on septic systems, even though they were within the city, and the road was quite cracked and deemed in need of repair. So during the summer of 2013, we had a connection to the sanitary sewers and a road repair project going on that street. And then in 2014, these street-side bioretentions and some front yard rain gardens and rain barrels were installed within the street. So we've just finished data collection on this project. For the 3 years that those paired watershed studies have been going on, we have been collecting discharge right in the storm sewers themselves. So each of these streets is what I call a headwater street. It is a headwater stream, except not really, because what we have is a centralized storm sewer going straight down the middle of the street. So all of the houses that you can see in this Google Street View, then their impervious surfaces are contributing to this storm sewer. So we're monitoring within the storm sewers itself just before these storm sewers drop off into actual headwater streams and ravines. And doing kind of a classic paired watershed study, looking at peak flows, runoff volumes, and lag times. Water quality component is being added to this project, but we don't have results to share yet. Just to give you a picture of what these green infrastructure are capable of doing at this street scale implementation. This is for one of our treatment streets, Klessner Avenue, and 2 quite similar storms. So the bars at the top represent 2 rainstorms. The blue is in our pre-treatment study phase. The red is after the first round of green infrastructure was installed. Similar antecedent moisture conditions. You can see it's a relatively short, intense rainstorm, but quite different hydrographs. Again, blue is pre-treatment, red is after phase 1 is installed. So a pretty substantial reduction in both peak flow and volume is possible with the street scale green infrastructure. If we look at our whole data set across the 3 years for those streets, it's a little more complicated. Unfortunately, in our pre-treatment year, we didn't have any really big rainstorms that we got in the data. And what we see here in this smaller set of storms is that there isn't very good differentiation between our pre-treatment and our treatment phases. But when we go out here to our larger storms, between phase 1 in red and phase 2 in green, we see quite a substantial reduction in peak discharges. Now, some of this, again, unfortunately, we didn't have any large storms in our pre-treatment period, but we also, having been out on those streets in numerous rainstorms, think that there's some physical explanations for what we see in this data set. When the storms are small and less intense, what happens is that the amount of street runoff that is generated makes only sort of a thin film going down the gutters. And in fact, we've noticed that the water tends to go straight and not make it into the bioretention cells. Whereas in the larger storms, we have a thicker flow of water on the street side and in the gutters, and we can see that the water is flowing directly into the bioretention cells and is really getting the benefit of the green infrastructure. So again, promising preliminary results that green infrastructure retrofit in residential streets can reduce peak flows, and I didn't show you volumes or lag times, but similar results there. However, we then have to think about what this might mean in terms of scaling up to the watershed. The West Creek watershed, where this project was done, is 36 square kilometers. It is 35% imperviousness. By our estimates, we've affected about 0.1% of the watershed with this project. So we're talking about pretty massive need to scale up to make a real difference on the hydrograph that we see in the West Creek overall. The other interesting thing that's worth noting is that between our two streets, on one street we got 12% homeowner participation, on the other we got 30% homeowner participation, even when all of this was free and maintenance was included for the first 2 years. So this suggests, and this is similar to what Bill Schuster's group has seen at the Shepherd Creek project down in Cincinnati, about 25% homeowner participation there. Again, at Stringy Bark Creek, they've seen greater homeowner participation, around about 50%, but a much stronger set of economic incentives. So this is where this human context and social environmental attitudes and economic incentive structure may really come into play in terms of limiting what hydrologic benefits we can see from green infrastructure. So we are in the process right now. These postcards and some accompanying surveys have been sent out to all of the homeowners on our streets to try to understand what is it that is influencing the perceptions and attitudes and interests of these homeowners about green infrastructure. So stay tuned for results coming there. Again, the other thing that we've noticed in doing this project is that very subtle things about the curb cuts, about the maintenance of these green infrastructure practices themselves can have some pretty substantial impacts on the performance of each of these. So that's something that we need to consider when we think about, again, scaling up the limited number of studies that exist on green infrastructure and thinking about how this might actually work in larger scale implementation. So just to summarize there, again, it's promising. We think there are some scaling challenges, and some of these scaling challenges may be as much about people and the way we construct and maintain these green infrastructure practices as they are about their hydrologic functioning. So finally, just briefly, I want to talk about this idea about trade-offs. Traditionally, stormwater management has really focused on peak flows and sometimes also on sediment and nutrient loading to the receiving water bodies. But now, as green infrastructure gains in popularity, and the concept of ecosystem services gain in popularity, we start to expect or maybe want more out of our stormwater management. Can we, for example, get habitat or carbon sequestration out of stormwater management practices? So a group of faculty here at Kent State have been having lots of fascinating discussions along these lines, and this represents sort of our first cut approach at thinking about a way to quantify ecosystem services and the potential trade-offs between them for different styles of stormwater management. So what I've got going on over here on this graph are a series of ecosystem services that might be possible from different styles of watershed and stormwater management. Again, traditionally our focus has been on water quantity and water quality, but we might take, and this is just a first cut selection, things like carbon sequestration, trace gas flux, habitat diversity, and cultural services as other things that people might want from stormwater management and green infrastructure. This graph shows our end members. So the blue line is a forested watershed. So the farther out you are from the center of the graph, the sort of better things are. And these are based on some unexisting literature and sort of expert elicitation on the values we might get out for these different ecosystem services. The red line here is the pavement pipe stream system where no stormwater control exists. So we really don't do anything for water quantity or water quality or carbon sequestration or habitat or culture. It's at least not a negative for trace gas fluxes. That's about all we can say for that one. The combined sewers, when they're not overflowing, they are somewhat useful in terms of water quality, and they are certainly useful in terms of reducing peak flows. So the combined sewers there are shown in green, but again, don't provide any of these other ecosystem services that we might want from modern stormwater management. So what about green infrastructure and sort of conventional centralized stormwater management? So the blue line remains. This is our sort of hypothetical forested landscape that's been replaced by our urban landscape. And so we see that based, again, on a combination of the literature and sort of expert knowledge, that various green infrastructure approaches might yield different benefits in terms of water quantity and water quality. And I should say that what we did here is we assumed that a bioretention cell, because there's a little bit of terminology in clarity here, that a bioretention cell was primarily coming off of a street and that it had an underdrain. So in terms of water quantity, we might be able to do something about peak flows, but we're not going to do much about volume reductions because that underdrain is going to pick up things rather than groundwater recharge. Whereas a rain garden in purple would be coming off a rooftop and would have no underdrain. So here you might be reducing peak flows, but also getting back to more of a pre-development water balance. All right, so similar sorts of decisions were made about water quality effects. Green roofs and rain gardens, because they are treating rooftop runoff, don't have substantial improvements on water quality that's going to be received by the stream, but something that's picking up street runoff might have more potential for improving water quality in the stream. All right. If we look over here at our centralized conventional stormwater management, we see quite different shapes. They might be very good at things like carbon sequestration and habitat diversity. And notice that the habitat diversity offered by a constructed wetland or a wet pond is equal to or better than anything we're getting from a piece of green infrastructure. But because of those wet aquatic environments, they're not so good on the trace gas fluxes front. So I think these diagrams, while rough, represent a useful first step in thinking about decisions we might make about what type of green infrastructure or what type of conventional stormwater management we put in depending on what ecosystem services are most valuable in that context of that watershed or a landscape, and maybe even are we willing to make trade-offs in terms of, say, our water quantity or water quality benefits in order to achieve something like habitat diversity within our urban watersheds? So I think I've fairly well exhausted the time. I want to just conclude with sort of putting this all back together with this overarching question of whether our conventional stormwater controls and our green infrastructure really succeed in minimizing risk to human health and infrastructure and protecting aquatic ecosystems. Fundamentally, it's about this stormwater stream connectivity process in which the things going on within the urban landscape, the processes happening within the stormwater control measure of whatever form, and how that's impacting the stream is the fundamental, but all these contextual factors are influencing how effective those stormwater control measures or green infrastructure are going to be at processing urban stormwater runoff. And then on the other side, there is this idea of trade-offs and different values. Are we prioritizing peak flows? Are we prioritizing restoring the more natural water balance? Are we prioritizing water quality? Or are we prioritizing something like other ecosystem services when we think about our approach to stormwater management? So then as we answer that big question, I would argue that none of the current solutions to stormwater management is a panacea because of these contextual differences and still things that we're trying to figure out about scaling green infrastructure approaches across the landscape. None of them is a panacea. And that really, I mean, this is the classic scientific answer. We need more science, that we need to continue to do these contextual process-based studies, particularly on the impacts of stormwater management on receiving streams, and that we need to really embrace the interdisciplinarity that's inherent in working in these human-environment coupled systems, working more hydrologists with ecologists, yes, but also hydrologists with landscape architects and social scientists to really understand what the potential limitations and trade-offs are of these stormwater management. And then to also work as a science practice collaborative and to be working directly with the agencies and the design groups that are designing and implementing different stormwater practices in our local areas and in the landscape, and seeing if we can both push our science forward and work hand in hand with the management at the same time. And with that, I'll be happy to take any questions.
All right, well, thank you, Anne. That was excellent. I particularly really loved those figures showing the trade-offs in ecosystem services, and I wish we would have had you on board for this proposal that we just had rejected from the NSF, but we talked about some of that stuff. It might have helped us. But let's move to questions. We've had several questions that popped up during the talk, and I'll work through these in the order they came in. And I think we normally try to end up at 4:30 Eastern Time, but we'll go a little bit long because we've got so many folks here and so many questions. So Aditi Bhaskar asked, why would a stormwater control measure produce more flow than other areas on a per area basis? Or am I not understanding the isotope results correctly?
Okay, great question, Aditi. You are understanding the isotope results correctly. In this case, we need to think about the heterogeneity within the watershed. So our impervious surfaces are not distributed evenly across the watershed. Our stormwater control measure is picking up a heavily impervious portion of the watershed, whereas some of the upstream contributing areas are, again, forested. And so in this case, even though the stormwater control measure is only draining 10% of the watershed area, it's draining a higher percent of the impervious surfaces. And that's what I think that we're seeing, this sort of outsize contribution from that stormwater control measure to the stream hydrograph.
All right, thank you, Ann. David Goodrich asks, are you making measurements on characteristics of the BMPs? For example, the KSAT of infiltration in garden, geometry, overland flow, rates, overflow rates, etc. He says that they've got modeling tools for implementing green infrastructure LID within a GIS and watershed model, but have found few good measurements of how BMPs perform.
Right, great question. Yes, we are. We are measuring lots of things. It depends on the project and the place, but for example, on the street side bioretentions in Ohio, we have been measuring hydraulic conductivity and soil moisture dynamics within those this summer. That was actually a summer REU project, so if you'll be at AGU in a couple weeks, there will be a poster in the Urban Stream session that Claire Welty is one of the lead conveners on. So you can check that out. There are a lot in the engineering hydrology literature. There are a lot of sort of input-output studies of different types of stormwater control measures. If we have a hydrograph that comes in like this, we can reduce peak flows by this percent, or we can take out 70% of the suspended sediment, say. But I think the trick is scaling that up to the street scale or the watershed scale, or really looking at what the impacts are on the receiving stream, and that requires more of the process-based understanding of what's happening within a particular BMP of some sort, and not just treating it as a black box.
And David followed up to say thank you, and that he's going to be in touch on the modeling tools. I would also add that I know Tim Fletcher, the Fletcher that we heard from a couple weeks ago, Fletcher and Walsh have been trying to get that kind of BMP scale. They've been doing studies at that scale as well as the watershed scale as well. So
Right.
I don't know how much of that's out there. That might also be useful to David. Okay, Sarah says, it seems to me that the distributed green infrastructure might have the potential to improve performance in the future as the plants become more established. You presented data from new systems. Do you have thoughts on the potential for improvement as the system ages?
That is a fantastic question, Sarah. Let's write a proposal and go after it. There isn't a lot of literature that I'm familiar with on how these green infrastructure systems performance changes over time. Your point about plant growth is important, and we did, for some of them, we did get sort of year 1 and year 2, and we actually made measurements of NDVI and percent cover and canopy height and things like that between the 2 years. So we do know that the plant growth is a big thing. In fact, we're getting complaints from the homeowners that these things are overgrown now, in their view. And we do know that in the ones with more mature plants, they tend to have lower soil moisture than in the ones with brand new plantings this last summer. So again, I'll refer you to my REU students poster at AGU for more details on that. So plant growth is one thing, so maybe we will see improvements. But the other thing that we are noticing is that even though these are draining streets, they're receiving a fair amount of sediment sort of being washed off the street. And so as these sediment are coming into the bioretentions, does that have the potential to clog the system over time or to degrade performance? The other issue is simply the maintenance of all of these things. So for the last 2 years, they've been maintained by a crew from Cleveland Metro Parks, who's been doing a lot of the work on this grant. But now that maintenance agreement is expired, the grant is over, and we're turning them over to the homeowners. And I have to imagine it's going to start to get a lot more heterogeneous in terms of what the maintenance, what the gardening will be, whether the fine sediment will be being removed. And so I think the long-term trajectory of green infrastructure in terms of its efficacy is a huge question that we need to answer. And if anybody knows of good studies that have already done this, I would love to see them. Otherwise, I'm going to be keeping tabs on these things for as many years as I can afford to do so.
I think, and actually, let me just add, I think that's excellent. In particular, it's going to be fun to see the failure rate, or how the performance rates change over time with individual homeowner responsibility for that management. This is, projects I've worked on, one of the most difficult questions from the communities, from local governments, is how are we going to make sure that these things are actually still working?
Right.
And I've not heard a great answer to that.
Yeah.
And okay, so Kate Sullivan asked, did you measure any other water quality characteristics, such as chemical pollutants or pathogens?
Yeah, that's a great question. Again, Kate, it varies by project. So in the Charlotte study, we have looked at nitrogen specifically, and then macroinvertebrates within the receiving streams. So I am a physical hydrologist by training, and my collaborators are sort of on top of that biogeochemistry and ecology side of things. So there's stuff coming out. I just decided to stick with my strengths for today. And then in the Northeastern Ohio bioretention project, we are focused on metals as our water quality indicator because, again, that's one of the things that we expect to see predominantly coming off of these streets. So we have the samples collected, and they're heading for the ICP within the next month. So again, stay tuned for those results.
All right. Then we've got a question here for your Austin versus Atlanta example. What role do you think differences in precipitation have on groundwater recharge versus geology? Or how might we separate from urban infrastructure?
Another good question from Aditi, who thinks about these things as well. You know, both of those places have this humid subtropical climate. I've never lived in either one of them, but I'm told the rainstorms are fairly intense in both. Atlanta in general is about 10 inches wetter per year than Austin. So, you know, that might not be the place or the pair of cities to look at differences in precipitation rate and distribution. We might do better to try and contrast something like Atlanta to something like Portland, Oregon. They are, off the top of my head, going to receive about the same amounts of precipitation over the course of the year, but at a very different distribution. You know, anybody who's been in the Pacific Northwest just knows that it just drizzles for about 9 months of the year. That's a really different precipitation pattern than something like Atlanta, where we get these intense thunderstorms. So I don't know of any studies that have tried to tease apart those two controls specifically, and I think it's going to depend on what you're looking at in terms of the hydrograph response. It may be that precipitation is really important for the peak flow side of urban hydrology, and the geology may be more important for the low flow groundwater recharge side of watershed response to urbanization.
Okay. We've got one final question we'll take here from Will. In northern cities, is the concentration of salt that makes these green infrastructure, makes the GIs and SCM make bioremediation, let me see if I'm reading this right. Is bioremediation inhibited by excess salt?
Right, so what's the salt doing to it?
Yep.
That's another good question. You know, we missed an opportunity with the bioretention because we've mostly focused on the summer. The flow stuff gets difficult to figure out when you're talking about snow and snow melting at different times and snow plowing things. But we should have put some specific conductance probes down in those storm sewers as well, just to see what the sort of uptake of salt is and whether the bioretentions are storing that salt during the winter and releasing it during the summer. I don't know. And again, I don't know of any studies in this area. If anybody who's listening does, I think that that's a really big question that I have is, are we just going to salt up these roadside bioretentions and make it more and more difficult to maintain the green side of them, and the ET that goes with that vegetation?
Okay.
Great question.
Well, excellent. And thank you very much. I think that was an excellent presentation. Folks, all 5 of these presentations will remain on the Quasi website, so if you missed one or you want to review something again, you can find them all there. Thank you, everyone, for participating in this series, and have a wonderful weekend and great holidays.
Thank you, Anne, for your presentation, and thank you, Seth.
Thanks to everyone for listening.